Okay. So, welcome again to today's lecture. So, today I changed a bit the topic with respect to yesterday and the previous days. The topic is, of course, strictly linked, but is somehow connected to what I said the second lectures. It is linked to primary cosmic ray sources. At some point, I divided the sources of cosmic rays in primaries and secondaries, saying that primary cosmic rays can be or are those particles produced directly in the sources, and we have seen the acceleration from supernova remnant shocks, or there can be some more exotic sources. We are not totally sure that they exist or they exist how we hypothesized, but a possible source is due to dark matter particles that act a pair annihilation. So I will introduce you somehow, even if very shortly, some basics about particle dark matter. This will be also the topic of the exercises that you will have today with Francesca. So this is the reason why I introduced this to you. And tomorrow we will come back a little bit to cosmic ray physics and how to solve the transport equation that will be true for any kind of sources in the galaxy. So let me say you few words about particle dark matter. Maybe you have seen some of this topic in the lecture last week. I don't know exactly. Nevertheless, the problem of dark matter, not only in the galaxy, in the Milky Way, but let's say the problem of the dark matter in the universe is now a very well established and I would say totally unsolved problem. We have evidences, we have gravitational evidences from many scales, from the subgalactic scale to the galactic scale and the extragalactic and the cosmological scales, that a big portion of the energy and content of the universe behaves as a matter, but totally escapes to our detection, if not gravitational. The strongest evidence that we have for the existence of this mysterious component comes from very large scale structures and the cosmic microwave background radiation. So the CMB, which is a relic from the Big Bang, has a spectrum, a temperature spectrum, which has very small anisotropies, and these anisotropies change at the different scales that you measure the CMB. And the fits to the CMB, so the comparison of cosmological models with the anisotropies, with the fluctuations of the cosmic microwave background radiation, cannot be done without a dark matter component. So this is a very strong result that we first got with the WMAP experiment, which is a satellite experiment now at the end of its lifetime, and subsequently by the Planck detector, again on a satellite. Planck as well as finished his mission, but from these two experiments we have strong evidences that some 20 and even more % of the matter content of the universe is under some unknown dark matter form. We also have strong evidences from the large structures in the universe. If we simulate the evolution from primordial perturbation up to redshift equal to 0 structures in the universe, we see that it is impossible to compare simulations and observations without dark matter. So these are very, very simply the reasons, or few reasons, that bring us to believe that a big portion of the universe is not under the matter as we know it. Similar evidences are from galactic scales. There have been measurements since the last 4 decades of rotational curves. The first one who started to measure and to interpret rotation curves in the galaxy, so how the velocity of the gas, for example, in a galaxy varies with the galactocentric distance, was Vera Rubin. She was one of the founders of this discipline. And also on galactic scales, we have hundreds of rotation curves that all indicate that at least at large radii, so distances from the galactic centers, we need some other component. Somebody is studying also possible deviation from Newtonian gravity. But anyway, the fact that we need some particle dark matter is, or some dark matter that then we try to explain by means of particles, is pretty well established. So let me write just a few numbers about the composition of the universe. We have that heavy elements, not hydrogen, but these are the elements we are built of, are very, very rare in the universe. So this is the number of the nuclei we are composed of. So we are not very well representative of what is the matter in the universe. Then we have neutrinos. You are attending the class with Professor Ferruglio, who is explaining you that neutrinos are massive. Even if we don't know exactly the absolute mass, we don't even the less know how the mass is given to this particle by nature. But some little amount of matter in the universe can be explained by neutrinos. And the amount of neutrinos that can fill the universe is negligible. I mean, it's not neutrinos that help us to explain the bulk of matter of the universe. Then we have, well, stars. Why not? We see them this evening. Stars are shining very nicely in the sky in Florence. And stars estimated, of course, not only in our galaxies, but in the galaxies that we believe fill the universe, are less than 1%. Then we have free hydrogen and free helium. They have both been produced by in the very early stages of the universe. The BBN dates back to few seconds, very few minutes after the Big Bang. And these guys are filling about 4% of the total balance of energy and matter of the universe. So you see that with the so-called baryons, of course, we neglect electrons here. Electrons are usually in the nuclei, but since their mass is 1/2000 the mass of a proton, cosmologists very briefly say that baryons also include electrons because of their very small mass. Well, and then the rest of the universe is made by some matter, which is dark because it doesn't shine at any wavelength, and we still don't know how it is really made. We call it dark matter, and it fills about 25% of the matter and energy content of the universe. So, not that less. And then we have an even more mysterious component of in the universe. I won't spend any time on this so-called dark energy, which nevertheless counts the 70% of the energy and matter content of the universe. So up to now, I mean, in my lectures, of course, we have discussed some topic about a very few percent of the component of the universe. Nevertheless, these are very important components in our galaxy and in all the galaxies similar to ours. However, there is this huge component that behaves as matter. So if you interpret all the cosmological data that I told you in terms of matter and not radiation, you have probably seen the two different equations. When you evolve, for example, the Friedmann equations, they are different from matter and from radiation. So they obey the matter equation. Nevertheless, we don't have specific idea on what it can be made of. We can make some hypotheses for this dark matter, and one hypothesis that physicists are discussing since decades is that this dark matter is made by a particle. In principle, it would work perfectly. I mean, putting a massive particle, I will tell you something more in the following, all the rotational curves and the large-scale structure and cosmological problems could be solved. There is only one not marginal problem to that, that is, this particle at the moment has not been discovered, so doesn't exist in the standard model of particle physics. So, we are left with two problems, not one. The problem that matter exists, and the problem that this putative particle solution does not even exist. This is, of course, an effort that our colleagues at colliders are pursuing, searching from particles, new particles that can behave as a dark matter particle. So what does it mean behaving as a dark matter particle? Well, this particle must, of course, have some characteristics. The first one is pretty intuitive. It should be stable. Otherwise, if it would decay, it would not be the particle dark matter now in the halos of the galaxy. So this dark matter particle must be stable, and stable means on scales typical of the age of the universe. So this particle should have an average lifetime of at least 10 to the 10 years. If it decays on scale of 10 to the 30 years, it doesn't matter because the universe would be much younger than that. So scales on above 10 to the 10 years. We know that the universe is about 14 giga-years old, and of course this particle should have at least the same age. Then, from this blackboard here, you understand that this particle should not be baryonic. Otherwise, it would have at some point interact with other baryons. And hadronic interactions, you know, produce particles, for example, pions, charged pions, neutral pions, then these are charged particles or produce photons that would have seen them. Even more so, if they were baryons, they would have lost a lot of energy, and this would not be the case because it would have not been so stable or at least collisionless. So it should be non-baryonic. We start to reduce some candidates. And then it should be neutral or almost neutral. So there have been recently some models explored by some theoretical physicists hypothesizing that this candidate could have a very, very small charge. But I mean, overall, it must be neutral. Otherwise, it wouldn't be dark. And it would also be collisional. Well, if we want, it explains the dark matter in the galaxy, it must be massive. I mean, we don't need zero mass particles, even if we discover some other particles. I mean, at the moment, the only massless particle that we know, of course, are gauge bosons, gluons, and photons. Nevertheless, we need a massive particle, and we need it to be collisionless. And the fact that it is collisionless permits the formation of halos and the galaxies and galaxy clusters as we know. The collisionless means that the only interaction that we can allow to this particle in order to explain the cosmological observations is that, well, of course, among the four interactions, it must have gravitational interactions, so be massive. And the other one is that we can allow this particle to have weak interaction. So, how can we solve this problem? Well, we have to make some strong hypotheses if we want to deal with dark matter particle physics. One possibility, which is the one that I will explore today, but of course the field contains a plethora of candidates and of models, and in your studies, in your career, you can, of course, afford them. And now I will discuss one of the most common studied candidates, which is also linked to the problems that I'm discussing at these lectures, which is cosmic rays. Okay, so this is my choice. One very, very generic class of dark matter candidates is called weakly interacting massive particles. So, nothing new except that we deal with the generic candidate, which is called WIMP. And if somebody is coming with theoretical physics models that explains a WIMP, I mean, this person is, of course, welcome. You have probably heard that in the past, and also partially at the present times. Some physicists are studying a theory beyond the standard model, which is called supersymmetry. This theory may contain candidates that are fully compatible with the Wink hypothesis. But of course, before being sure that this is the case, we have to discover it at accelerators. And so far, LHC has not produced any positive signal. So we are, from one side, making a lot of efforts on the cosmological experiments, trying to study these particles at accelerators, and so on and so forth. I will also discuss you some more possibilities to detect these particles. But before coming to that, let me add a little bit of information about this possible particle. Well, if you do, if you compute with thermodynamics equations, substantially with the Maxwell-Boltzmann equation, evolution of particles in the universe, and you do also for this particle, you can arrive to a solution for the relic density of this particle. The relic density is the density of this particle that we measure today with respect to the critical density of the universe. This parameter, I don't know if you have discussed last week, anyway, I remind it. It is called omega, and omega for any species that I label I is its density with respect to the critical density of the universe. So we have a omega, a relic density for the neutrinos, an omega for the baryons, and an omega also for dark matter. The critical density of the universe is computed via this equation that one derives, for example, from Friedmann equation, and that corresponds to the density that the universe would have if it was flat. That seems the case after the data that we have from cosmology. And if you put numbers, H0 is the Hubble constant measured today, G is the Newton constant, so everything is just numbers, and one can find the values, which is 10 to the minus 29 grams per centimeter cube. In other units, it is about 5, 10 to the minus 6. You have, in this case, GV, C squared, per centimeter cube. Or even in other units, we have 1, more or less, 1.3, 10 to 11 solar masses per megaparsec cube. So look at these numbers and try to figure out how dense is the universe on average. So again, this is the critical, the density that the universe has because it is flat. That means that if we take portions of centimeter cube, we find 1 proton over, let's say, more or less 1 million of these cubes. So it is not that dense on average, the universe. Or if you prefer, look at this number. Our galaxy, the Milky Way, is just an average spiral galaxy. There are much smaller galaxies. There are giant elliptical galaxies. So we are more or less in an average range of mass. And the Milky Way is 10 to the 12 solar masses. So that means that on average, in the universe, in a cube of megaparsec size, we find less than 1 Milky Way. And our Milky Way is, We have neighbors at, I would say, maybe 700 kiloparsecs. I think that Andromeda is more or less this distance. So the universe is on average much less dense than our environments, and it is made by components that we substantially don't know. So this is, of course, a wonderful news for you. You are at your young career, you are just beginning to do physics, so I would say that there is a lot of work for you. Just decide which sector you want to explore, but neither we have explanation for dark energy, neither for dark matter. We probably need new particles, but we have not found that accelerator, so plenty of research. Let me come back again to a few numbers. I was saying that if one takes the equations for the evolution of particles in the universe, starting from the very, very early phases, we can compute the relic density of the particle. This is the relic density of this particle that I will indicate with a short label chi, and h is the reduced Hubble parameter, so it is a number that we know more or less. H squared is 1/2 because h is close to 0.7. Okay. So these computations lead to omega h squared for the dark matter, which is 0.1. And then we have 10 to the minus 26 centimeter cube per second. And this is the normalization. Let me put here a subscript, which is an V. So let me explain these results. Again, this is the solution of a Maxwell-Boltzmann equation for the density of the dark matter. This parameter, omega h squared, is connected to the density of the universe. These are practically the omega of any species, because for a critical universe, omega is 1, and you see that these numbers, since our percentage, are summed to 1. That means that the corresponding relic density for dark matter is about 0.25. Okay? Now I'm calling it key, and it is more or less 0.25. H squared is 1/2, because h is 0.7, just approximately. So this coefficient here is more or less the measured dark matter density if this number is close to 1. This number is a normalization, and this is the annihilation cross-section. That means that these two particles, if are present since the beginning of the universe, so are present as the components, the elementary particles in the universe, can annihilate each other's, giving anything that we will see. But, of course, if they annihilate at a very high rate, we wouldn't have almost any particles left now. So this annihilation cross-section, this is mediated, this is, averaged on the velocity distribution of these two particles. So this number, in order to give the proper relic density, must be close to this normalization factor. So I already gave you the numbers that produced the omega that grossly is what we need from cosmological data. Well, let's look a little bit more. This is a very strong connection of particle physics and cosmology. And then I will give you some connection to astrophysics. So we want that this number is not far from 1 to produce the correct relic density. These particles in the universe, in order to produce the correct structures that we observe by means of deep surveys of clusters and galaxy clusters, and of galaxies, sorry, this data tell us that the dark matter particle we are looking for must be cold and not hot. Cold and hot are two definitions of the kinematics of this particle when they decouple from the primordial plasma. Neutrinos are relativistic and they are hot particles. These dark matter particles, these WIMPs, must be cold. And cold means that their velocity must be more or less 10 to the minus 3 the speed of light. So, non-relativistic. So, I want now to derive the requirement on this annihilation cross-section, given that this factor here is close to 1. So that means that very approximatively, we have the number, which is 10 to the minus 26 times 3. And this is divided by the speed of this particle. And these are centimeter cube per second. And then we put c, the speed of light. And finally, you find that this number goes close to 10 to the minus 33 centimeter cube, or it is of the order of nanobarn. So you have studied interactions, electromagnetic interactions, strong interaction, and weak interactions, electroweak interactions. Which are the typical numbers for this kind of cross-sections? I gave you the Thomson cross-section yesterday, and we have seen that it is 0.6 barn. And now I did this work. I took the particle data book, the particle data PDG, particle data group, and there is the catalog of all the cross-sections that you could dream, that have been measured, of course. And we can find this plot. This plot is in millibarn. So I put this bar at the nanobarn level, which is the section, the cross-section that we would require to this particle to be right what we want for cosmological behaviors. And you see very grossly that this cross-section is typical weak cross-sections. This is the Z resonance in E plus T minus collisions. So the cross-sections of the order of the nanobarn, the more the less, are weak cross-sections. Somebody calls this coincidence the WIMP miracle. It is not a definition that, I'm not very enthusiastic about this definition, but of course, it is a very curious coincidence that the particle we would need in order to explain the relic density of the particle seems to require weak interactions. And so this WIMP, this W that I wrote before, has this meaning. And for these reasons, scientists keep going on in searching a new weak interacting massive particles. How do we search these particles? Because, well, it's nice, but we should have some evidence. And there are three ways, I would say, at the moment, that scientists are exploring in order to try to discover some new particle behaving as a relic of the Big Bang. Well, first of all, if you want to, maybe Dario, we can move to the blackboard? Okay. Okay, thank you. Yeah, sure. The first thing that we must do if we want to be sure that a new particle exists is to produce it at colliders. There's no other way so far. Producing it at colliders means that you take some standard model particle. Now the LHC is working with protons colliding to each other to study some interaction, giving these particles in the final states. Also at colliders, this is not an easy task, because if particles have no electromagnetic nor hadronic interactions, also at colliders it is hard. And if these particles exist, and if these particles are produced, for example, will be produced at the LHC or at another collider, they won't give any light, they won't produce any charge, hadrons decaying to muons, and so on and so forth. So they usually, they are usually predicted to, how to say, it's kind of oxymoron, to manifest themselves with energy missing, which is a bit hard in very complex hadronic jets looking for energy missing. But this is the hard work that our colleagues at experimental physics are doing, exploring models and, of course, modeling in a very precise way the background. Because now I think you have understood that weak signals are weak. And weak signals are very often covered by huge backgrounds. This is true everywhere you try to look at a weak signal. I mean, with electrons, it's a bit more easy because they don't produce hadrons. But if you are in any background in which you have hadronic interactions, that is a mess. So this is one big effort that our colleagues and also the community overall, the international community, is pursuing to look for new particles, and in particular massive, neutral, stable particles that can be relic from the Big Bang. But let's make the very, very happy hypothesis that LHC discovers a new particle, and this new particle is this way, is massive, is neutral, is stable, so it is not the Higgs boson. And, well, you take your very approximate formula, you say, okay, it could be a relic from the Big Bang. But we have to check this. Even if we produce at colliders, we must be sure that then nature has chosen it to produce the galaxies and the cluster of galaxies that we observe. And for this reason, there are other two ways that people undertake to measure this. And one is the so-called direct dark matter detection, and another one is the indirect dark matter detection. So what is the direct dark matter detection? This is the very precise way to measure if a particle coming from space is behaving as a dark matter particle. And it is given by the weak interaction of a dark matter particle with a standard model particle recoiling and just leaving as a sign of its interaction some recoil energy. The direct dark matter detection is another very huge research field. In Italy, we have at the moment the biggest underground laboratory in which these searches are undertaken, which is the Gran Sasso laboratories. Other labs are present in other countries. This laboratory was built by INFN. Since you are in an INFN institute, I can tell this. In the 50s, it was built expressly for doing research, and it was already foreseen some tunnel in the CERN direction. So it was a very brilliant idea of some colleagues many decades ago. On the other side, in many other places of the world, there are dismissed mines that are reconverted to underground laboratories. And of course, there are experiments also working in these places. So far, we have not any clear signal for the presence of a recoil energy that is clearly assigned to dark matter, but I mean, it's a very interesting and very lively field, and we wait for some data in the following. And then there is a much more involved way of searching dark matter, which is the indirect dark matter detection. I told you that these particles in principle can annihilate in pair, and if this annihilation happens in the first stages of the universe, I mean particles are particles and should also annihilate now in the halo of the galaxies. So one possibility is to study the annihilation products of two dark matter particles destroying each other's and giving standard model particles. This is the connection to the lectures that I gave yesterday and the previous days, and I will give in the same in the next days. So, two particles constituting the dark matter, let's for simple to think to the halo of the galaxy, of the Milky Way, I mean, annihilating each other's. If this is an elementary annihilation, the standard particles are elementary particles, quarks, gluons, electrons, photons. Nice. I mean, it would be wonderful to find some signal emerging from a background. And the background is right what I was trying to explain the last days. The background are the plethora of particles that our galaxies produces anyway, because there is gas, because there is stars that originate, then die, and so on and so forth. So the indirect detection is the search of dark matter annihilation products in the cosmic radiation. And now we have the problem. Where are the best places, or which are the best observables that we can look for? Well, let me show you a couple of pictures. One is this one. I wanted to, I mean, not I wanted, I could have shown you yesterday, but maybe here it is a bit more striking. So this is a partial compilation of data of cosmic rays measured with detectors at the Earth or in space. It is just a selection of the most recent experiments, which are Pamela. Pamela is an experiment on a satellite, which now has finished its lifetime. It was mostly an IFN collaboration. Then there is AMS. AMS is a big experiment installed on a space station. You have probably seen also some pictures, because this big AMS detector, which is a kind of accelerator, typical accelerator detector, so it's silicon tracker and so on, had to be shipped on the International Space Station only with the shuttle. And it was installed on the last flight of the last shuttle. And I mean, thanks to this last flight, we can now have a lot of data from this beautiful experiment. Some others, as DAMPE, are whether on satellite, or there is not listed here, but another small experiment installed afterwards on the International Space Station. The message is that most of cosmic particles that we measure at the Earth are protons. And this is just a similar percentage as protons and helium at the beginning of the universe. So it's not that different. So you see that there are protons, and it is pretty stupid to look for protons from the dark matter annihilation. There are so many that we cannot have any possibility to detect some exotic component. Then there is helium, which is more or less 1/10 of the protons in the cosmic radiation. Again, it is a lot. Then we have electrons. And look at here. We also have the detection of a number of antiprotons and the number of positrons. This is antimatter. Antimatter is detected, is produced at accelerators and detected in cosmic rays. The ratio of positrons over electrons is pretty high, is some 10%. The ratio of antiprotons to protons is some 10 to the minus 4. But let's discuss this figure, which is another way of seeing the previous one with some addition. We have here plotted as a function of the energy, sorry, I didn't put credits, but it is a figure made by Luca Baldini, and it is present on one paper by him on arXiv. We have the ratio, you see this one, this is what I showed you in the previous figure. This is the ratio of the antiproton to proton flux. That means that more or less it is of the order to the 10 to minus 4. So it is strongly suppressed. The ratio of positrons to protons, which is important because they have the same charge. So one must have a detector able to measure the mass and not only the charge, otherwise you mix the two. And again, this is pretty small. Antiprotons over electrons, so same charge, well, have a peculiar trend here. But what I also want to underline here is the ratio of all the photons that we expect to be produced in the sky. I will devote some time to photons with respect to protons. And the ratio is very small, is some 10 to the minus 5. So you would say, okay, why should I look in general at photons, in particular to some photons coming from strange sources? Well, photons are nice guys in the sense that they keep the direction of their source. They are not, so all the stuff that I discussed for 3 days to you doesn't work for photons. They are neutral, they don't diffuse. So if some of you comes today and tells, well, I have a prediction that there is a place in the sky in which dark matter is extremely dense because you have your model. Well, the best things to do is to take a gamma ray telescope and to point to this direction in the sky, because all the photons that could be produced by the annihilation of these two particles into photons do not diffuse, do not disperse. So you point your telescope there, and you should find a huge number of photons. You move your telescope around the source, and again, the flux would drop to, let's say, the background level of the flux. So the fact that gamma rays, also neutrinos, I won't spend so much time to neutrinos, but that's true as well for them, keep the direction, is very interesting in the search for indirect dark matter signals. So the particles that we are studying as possible indirect signals for dark matter detection are antiprotons, because they are very suppressed by nature in the cosmic radiation. They are positrons, even if they are not that small. If I have time, I will show you something to you tomorrow. But anyway, there is a big portion of the positron spectrum that we don't know how to explain. And so people thought maybe it is due to dark matter annihilating into positrons. This is not the only possibility. We have seen together that also pulsars produce E plus E minus, but nevertheless, this is a channel that has been explored and still under scrutiny now. And then there is something that I will probably not discuss in these lectures. A bit is not true. I'm very aficionated to the antideutrons, because when I was very young researcher, more or less your age, together with other two colleagues, we proposed the possibility that dark matter could also produce antideutrons in cosmic rays. And after some few years, now there is a small experiment devoted to the search of antideutrons. AMS has the possibility to look for antideutrons, but there is a dedicated experiment under construction at NASA, so in the following years we will probably hear something about this channel. And then we have gamma rays, which are extremely interesting. The exercises that Francesca will lecture you today are about gamma rays, and in particular gamma rays from dark matter detection. And one other possibility I told you that I won't explore that much are neutrinos. So these particles here are charged, and once we know their source, they enter in the diffusion equation that I discussed to you yesterday. So it is a further source if you believe that they are there, if you want to make some hypothesis. So now I go very quickly to one of the properties of dark matter, because Francesca will go into more details this afternoon with you, which is to understand the sources for this dark matter. So at some point, I don't want to rewrite now the diffusion equation, but the source was a term Q as a function of the energy and as a function of the position. Now I wouldn't consider the dependence on time because these particles are there since a while, so it's not, of course, a variable source, the one of dark matter, the relic dark matter. Nevertheless, in order to put some viable expression for Q, let's say Q is the source term in the diffusion, in the transport equation of cosmic ray. So Q, due to primary sources, in particular, identified with the annihilation of two dark matter particles, depend on energy and on space. And now I will give you a couple of details on this, and you will explore better with Francesca this afternoon. So, how can be the spectrum, the energy spectrum of two dark matter particles? For primaries accelerated by supernova remnants, we derived the first order Fermi acceleration, and I gave you all the computation. Here, the physics is totally different. So we have two dark matter particles. They are fundamental particles, as electrons, as quarks, and they annihilate in elementary particles. And these elementary particles, depending on the particle physics model that we have, can be quarks, gluons, photons, neutrinos, and leptons in general. So, in a very generic way, we can write the energy spectrum. So we have two dark matter particles that annihilate in some particle I plus whatever. This I can be antiprotons, can be positrons, can be gamma rays, whatever we want to look for in our cosmic radiation. And the very generic formula is that, in principle, it is a sum on all the possible F, which is the annihilation channel, so you can produce the same particle exchanging a Z boson or exchanging another particle. So it is really linked to the particle physics models. Let me write and then comment. Okay. So maybe I give you one example so you can understand then the more generic one. So let's make the hypothesis that I is antiprotons. We can have antiprotons by the fragmentation of the H particle, which is, for example, a couple. So if I is antiprotons, H can be Q bar, or can be gluons, for example. And these elementary particles can be produced by different, let's say, Feynman diagrams, different exchange particles, and also if the channel is S or T or U. This physics is elementary particle physics. The term B is the branching ratio into this specific final state. So the branching ratio is, well, whether you have a full model means that you can write a Lagrangian with all the couplings, with all the masses known, and then if you have your Lagrangian, you have your gauge theory, you write down the all the observables, including the branching ratio. So this is one possibility that physicists, of course, explore. They have a particle physics models and they predict branching ratios. Another way is to say, well, I don't know exactly the particle physics models. I only make the hypothesis that this is weak interacting, it is massive, and you make an ansatz for the branching ratio. Usually people say, okay, let's assume a branching ratio to antiprotons via bottom, anti-bottom hadronization equal to 1. So this is a choice of the researcher and the possibility different possibility to explore also the comparison with the data. This is for the spectrum. The energy spectrum, this is another piece of work. So how do this particle can hadronize to antiprotons when, for example, BB bar, they are produced from two weak interacting particles? Well, the prediction for this term is usually performed via Monte Carlo simulations, via Monte Carlo codes. Maybe you have heard about the PITIA, Monte Carlo codes, the Herwig Monte Carlo codes. These are very huge efforts that people have undertaken since few decades to interpret the accelerator data, and we can use also to simulate the spectrum of final particles produced by two weak particles. You will see something about these particle physics problems in the afternoon. But then we have another problem. So this is, let's say, a particle physics sector work. But this vector R here is linked to the distribution of dark matter in your galaxy or in the universe according to what you are looking for. And this is a purely cosmological problem. And this is the problem linked to the dark matter distribution. This is, again, a very, very complex problem. The prediction of how dark matter particles distribute in the universe and in the galaxies. So far, the best way that we have to predict the particle distribution in the galaxy is cosmological simulations. So there are these big code working based on n-body simulations that with the fundamental ingredients of cosmological perturbations and some amount of dark matter and some amount of dark energy and so on and so forth, try to evolve from the very beginning of the universe to even redshift equal to 0 and simulate the formation and the distribution of structures in the universe. Again, these are very big scientific efforts. There are some groups in the world working on that. These groups, of course, must rely also on a huge numerical power, because these simulations are really time-consuming. Nevertheless, we have results from different groups. In the last years, these simulations have also been refined because the researchers are starting to put some more small-scale baryonic physics that should modify some prediction of the past. Anyway, the outcome of these simulations are manifold, but what is interesting to us is to see how this particle distribute in space. Well, in principle, also in velocity, but often this velocity distribution is hypothesized to follow some simple behavior. The distribution of particles in the universe or in the galaxy goes under, of course, a function which is a density function of this particle as a function of r. Now I just remind you that at galactic scales, and not only at galactic scales, but even in a more generical way, the distribution of dark matter, now I put the formula in spherical symmetry, so I only write R. Probably the halos around the galaxy are not perfectly spherical. Nevertheless, this is the hypothesis here. Let's write this for the Milky Way. The distribution of the dark matter, this is the distribution of dark matter. R is the galactocentric radius. So in the galactic center, R is equal to 0, and so on. Is given by some normalization factor, some R over R, and 1 plus, let me write this and then comment. This should be gamma. In my notes, I will provide you my written notes, okay? So I don't have, I was telling Dario, I don't have LaTeX notes, but I think that my way of writing is not that bad, so you can understand. No? Maybe I win the award of good calligraphy, or all my colleagues. So, yeah. It is understandable. I think that the notes are this way, and if you are interested, you can read. So this is a generic way to write the profiles of dark matter, mostly at the galactic scale. These are coefficients, alpha, beta, and gamma, that changes according to different predictions. There is a profile, a radial profile of dark matter, which is called the Navarro, Frank, and White profile, according to the three authors that first derived from simulations, from numerical simulations. And it is one of the most used profiles, and it has 1, 3, and 1. And Francesca will elaborate on this in the afternoon. There is another profile which is also used, which is more empirical, and which predict a core. I will come in a while. Pseudo-isothermal, in which the coefficients are 2, 2, and 0. So, let me tell something more about this. This is written for the galaxy. That is, it is normalized to this rho. Anytime you see this dot circled, means at the position of the sun. This is the astrophysicist convection. And this Density is measured here locally, so at the position of the sun. The position of the sun with respect to the galactic center, well, this is, I mean, a bit a variable number. It is kind of, when I started to do the research with my PhD advisor, he told me the distance of the sun to the galactic center is as skirts. Sometimes they are shorter, sometimes they are longer, according to the fashion. And shorter or longer means between 8.0 and 8.5 kiloparsecs. So since, I mean, it's out of jokes, this is a measurement which gets continuous improvements because of kinematical data, rotational data. There are some huge compilations that came out in the recent years. So if you want to be very precise, just check the very last literature on this point, because the activity is pretty lively. But well, I think that in my last papers we put 8.33 kiloparsecs, because not because we are Solomonic, but because these were numbers, published numbers. So this is these are the numbers. Let's say 8.5 or something like that kiloparsecs. And then the density of matter at our location, at the location of the Earth, again, is something which is continuously evolving because of new determination, but it is about 0.5 GeV per centimeter cube with some errors, which again depends on the determination that are done by different authors. So at the location of the Earth, there is less than 1 proton per centimeter cube on average. So everything is mostly empty indeed. This other parameter, which is here, is a typical scale radius, which describes some specific radius, some specific length of each profile. So there is no fixed number. In the Navarro-Franken-White profile, this number is of the order of 25 kiloparsecs. Instead, in this other possible distribution of dark matter that is more phenomenological, so it is mostly derived on rotation curves, this parameter is few kiloparsecs. So you have to keep all the parameters as very specific of the dark matter profile. The most recent simulations have also outlined that many halos, dark matter halos, not only in galaxy but also at different scales, follow another profile which is called a NASTO, according to a very old proposal by this physicist. And I just write you as it comes out from the determination of our simulations colleagues. So it has a normalization factor that people call rho -2, and it has an exponential trend, which is given by -2 over alpha, and alpha is the free parameters that you fix with on the simulation. R is normalized to a typical scale radius that they call R -2. And this is again alpha -1. And this R -1 is linked to the logarithmic density taken at -2, equal to -2. But I mean, it's not something that I want to discuss today, you can find in papers. But this is the result, the plot that you can very easily also perform yourself. Anyway, these are, grazie Dario, the functions that I wrote on the blackboard. This Burkett profile is very similar, can be reconducted to this chord profile. So the fact that it is chord is visible here. This is the position of the sun. It is 8.5 more or less kiloparsecs. This is the galactic center. And the profile, the chord profile, is more or less flat since few kiloparsecs till the very center of the galaxy, and then it decreases. Well, now it is not very visible because it is a log scale, but very, very steeply at very large radii. And these are the two profiles, the Einasto one, which is increasing toward the centers but has no divergence. Instead, the Navarro-Franke-White, since gamma here is 1, has a mathematical and divergence and also a physical problem at the very center of the galaxy that one tries to treat with some tricks. I don't spend time on that. So you see that these are very different predictions. They are all normalized to the local density. And what I want to underline with this figure are two things. One is not very visible, but the halo of the Milky Way, the dark halo of the Milky Way, is predicted to have a radius which is even larger than this number. It is about 200 kiloparsecs radius wide. So the Milky Way from, let's say, simulations, is predicted to be, well, the fact that it is a spiral galaxy is an observation, but a galaxy with a disk of baryons, stars, and gas. The Earth is here. This radius is about 20 kiloparsecs. The visible matter is distributed in a disk whose length is about 20 kiloparsecs, and it is immersed, it is filled, it is set in a big, big, big dark matter halo whose typical radius is 10 times larger than the scale of baryons. So my picture is awful here, but I'm sure you have understood. So this is the first message from this kind of plot. The other very interesting message is that what does it happen at the galactic center? And the answer is it depends. It depends to what dark matter distribution you assume. If you assume that it is a chord dark matter profile, as a number of astrophysicists believe, this chord profile fits pretty well a huge number of rotational curves. Well, at the center of the galaxy, we don't predict, this profile does not predict a huge amount of dark matter. The other two profiles, which comes from simulations, so they have fundamental physics inside, they predict that the dark matter towards the center of the galaxies should be very much increased. This is why physicists have tried to look for dark matter in the gamma ray indirect signal, because it doesn't smear out the signal, at the center of the Milky Way and also of other galaxies. The point that I still want to mention to you is that these simulations predict the formation of hierarchical structures. That means that this is a profile for, in this case, for the Milky Way. But the simulations do not only predict halos of the galaxy, but also predicts that galaxies cluster, but also that galaxies have inside their halo smaller halos that we call sub-halos or substructures. So according to this simulation, the structures in the universe are from smaller ones to very big ones. And each of the structures, at least till the simulation of the resolution of the simulation is, makes it possible, follow generically these laws. Okay, so now we have some instrument, at least some theoretical instrument, to write a formula for the fluxes of particles that are produced from dark matter annihilation and that we expect on the Earth. And I start from the, I don't know if it is the simplest, but at least it is the signal that doesn't need any transport treatment, which is gamma rays. And this is the formula that it will use this afternoon for some exercise to you. What I'm writing here is the flux of gamma rays from dark matter annihilation in the galaxy. Or, I mean, it is indeed generic what I'm going to write. This flux, I call it phi gamma, and its dimension, if you go to the very first information at the beginning of my course, is a number of photons per surface, let's say centimeters cubed second, steradiant GV. Anyway, when you will deal with these fluxes, be very careful to the units, because sometimes people call flux but have integrated over a solid angle, so you miss a steradiant or 4 pi. So in general, be careful mostly on the angular part. Anyway, this flux of gamma rays is a function of the energy, and it is a function of an angle under which I point my telescope. So this is, I don't know, Dario is the source of our gamma rays, and so I point, I point to the source. Since gamma rays are photons, they run a straight line, and this angle is the aperture around this line of sight. You can open your observation of one few degrees, or depending on the interest that you have and depending on the telescopes you are working with. So this flux is 1 divided 4p, 4 pi. Then we have the source. The source is the annihilation cross sections times velocity averaged on the velocity distribution. And then we have divided by the mass squared. And we have the spectrum of gamma rays. I hope to use the same notation. Let me check as before. Yes, dN over dE into gamma rays. And then we have the space information, because this is just one part of the source term for gamma phase. The other part is an integral along the line of sight. This is the line of sight. Traditional is better than laser pointer. And then we have the density squared, and the density is just what I've discussed here, and it is squared because one particle comes with its density and the other particle comes with the same density, and they collide each other. This is a function of the distance, but the distance in terms, I will just write in a while the definition, of lambda, and lambda is the line of sight. The angle is psi, and we integrate along the line of sight because, well, maybe you are not the only one in the universe, so there could be some other sources of gamma rays. So if I integrate from me to the source, there could be that other smaller or different sources are present along the line of sight. And this permits to compute all the possible sources on this line. And as I was telling you, it depends on the operation, but there is also a possible integration on the aperture angle, which we are calling psi. Good. So let me draw a very simple plot. This is our position, or better, the position of our telescopes. This is the galactic center. Usually coordinates are given in galactocentric ones. We have a source here. The line between us and the source is lambda, is the line of sight. The line of sight is this direction, and lambda is the line of sight taken from us to the source. Line of sight is the direction that joins the observer and the source. This is, sorry, maybe I told you before aperture, but it was not the correct definition because this is the angle in these coordinates. In galactic coordinates, this point, I don't know if you can see, but if you project this point into galactic coordinates, we have the distance, which is r. This is the latitude, and imagine this is on the plane, it is the longitude. So if you have to do some computations, you will check your geometry, but this is just to say that we have some coordinates which are referred to us because we have the telescopes, but then all the results are shifted into galactic coordinates, in which this angle cos psi is cos L cos B. I think I wrongly called it aperture, but it is the angle really linked to the geometry of the source in the galaxy. I was saying aperture because usually then all this flux is averaged on the aperture of your telescope. So it was kind of Freudian. Okay, this quantity which is here, the first one is a typical particle physics quantity. So in order to compute it, you must know, in principle, the Lagrangian, the full field theory that predicts you this particle. Or anyway, you have to make an assumption on the mass, on the annihilation cross-section, and on the final states of the annihilations. This is instead a factor which is linked to cosmology. You need the two to make your prediction. Grazie. So, this factor, this cosmological factor, is in the literature usually called the J factor. It's just a jargon, because some authors named this way some 20 years ago. And I define once, and then you will probably study it again this afternoon. This J factor is normalized to the distance, which is 8.5. It is normalized to the local density. And it is the integral along the line of sight of this rho squared. Lambda is a function of an angle phi, or lambda psi, the lambda psi. This is the J factor, and you will work on this this afternoon. Usually the visibility, the luminosity of a dark matter source is given in terms of the J factor. So if a source, which is a galaxy, which is the galactic center, which is a dwarf galaxy, has a very high J factor, that means that there are more hopes to see photons due to the annihilation of the dark matter inside this source. And I can finish this lecture by showing you the maps of J factor. The first one has been computed by Francesca, myself, and other collaborators. And the other one has been computed by Bonivar and Morin and other authors that have written a code. The code is called CLAMPy, and it computes the J factors in many places of the universe. These are galactic J factors. So this is the J factor. These are the units, because it can be or not normalized according to authors. Anyway, if computed in the hypothesis that the halo of the galaxy is smooth, there are no substructures, there is only one spherical dark matter distribution following the Einasto profile. And you see that, as expected from the previous figure, this profile is very peaking in the center of the galaxy, so that means that the color red here means that the J factor is much higher towards the center of the galaxy. So if the galaxy were made this way, well, the only hopeful place to have a strong signal would be the center of the galaxy. Also at other latitudes, it is interesting to search for dark matter, but one must be a bit more careful to compute all the backgrounds that are present. If, as all the simulations predict, there are smaller structures, also these subhalos in the galaxy have their own distribution that follows inside an Einasto profile. So this is the distribution of subhalos predicted for the Milky Way that have these J factors. So red here means very dense. This is a simulation, again, for the J factors computed towards the anti-center of the galaxy in a square of 5 times 5 degrees. And again, you see that the white here is connected to very dense halos. So this is the distribution of dark matter that we expect, and as well the distribution of photons if we were able to measure them with a telescope as clean as this figure is, which is not always the case. Okay, so have a good lunch and see you tomorrow.